Hello everyone, I am Roggiolani and today I will present you my work on domain-specific pre-training for effective semantic perception in agricultural robotics. In the last 70 years, the world population has grown from 2 billion to 8 billion of people, and this number is only going to increase. To face the augmenting demand of resources, we need to produce more food than ever and in a sustainable way. One possibility is using robots to automatize the agricultural procedures. For robots to help us, we need them to understand their surroundings. For example, what is a crop, a weed, a plant, or a leaf. In order to do so, we need to train neural networks with labeled data as the one shown in this picture. Unfortunately, labeling data is time-consuming, error-prone, and a lot of effort. We propose to reduce this effort with a domain-specific pre-training. Starting from our dataset, we use two sets of augmentations to produce two different views from the same image. Both the images are passed through the network to produce one embedding for each one of them. Then these embeddings are normalized along the feature dimension and the cross-correlation is computed. The loss we use is force the cross-correlation of views coming from the same image to be 1, while the cross-correlation of views coming from different images to be 0. This architecture and loss were originally presented in the paper Barlow twins from ICML 2021. We make the Barlow twins approach domain-specific, changing two important steps. The first one is the dataset that we use. We pre-train only on images coming from the agricultural domain. The second step is the augmentations that we choose. We use both common augmentation strategy as the affine transformation or the Gaussian blur and new augmentation specific for our domain. In particular, the background invariance is a new augmentation that we propose, while the color and mix are variation of existing augmentations that we change to adapt them to our domain. In the background invariance, we use a vegetation mask to extract crops from one image. We apply a random translation and rotation and then paste it onto another background. This results in a new image with a different soil and light condition, plus the different position of the crop. The standard color augmentation applied in the literature can have outcome like the one on the right, which is not realistic and does not help the network focusing on the crops. We change the range of the transformation so to always have realistic outcomes that can really be encountered in a field. For the mix augmentation, we flip the image on the x and y axis and use the new images to simulate the presence of more crops or different crops in the same image. To evaluate the augmentation proposed, we pre-train using all possible pairs in the two possible orders, and then fine-tune for semantic segmentation. The blue table on the left is the result where the number expresses the mean intersection over union. Lighter color indicate lower performance and darker color indicate higher performance. We can see that not only the order of the augmentation matters, but that the best performance are obtained with domain-specific augmentations, like the background invariance, or with very strong augmentation, like the random erasing. We also point out that some of the experiments required more time to converge. Those are indicated with the asterisk, the star, and the dagger, which corresponds to 10, 20, or 30 more epochs. On the right, we compared our color augmentation with the one from literature, retraining only with those augmentations and fine-tuning on semantic segmentation. We see that at first the standard augmentation, which can have a very strong impact on the images, has better performance, but the more we pre-train, the more the standard augmentation gets worse, while our augmentation keeps on improving, since it presents to the network variations that it will actually see during the fine-tuning and evaluation. Our final experiment on semantic segmentation compares our pre-training to other strategy as pre-training on ImageNet, pre-training on domain data but with the augmentation from the literature, and with the network without pre-training. We can see that with few labels, the ImageNet pre-training hurts the performance, since the network has no knowledge about the agricultural domain. Using domain data already gives a significant boost, but the best results is obtained combining domain-specific data and augmentation. This can be also seen in the qualitative images, where the first column shows the result for the network without pre-training, the second column the network pre-trained on ImageNet, and the last column shows our result. We also evaluate on leaf instance segmentation, which requires to assign an instance ID to each leaf in the image. In the plot, we see that the difference in count is the absolute difference between predicted leaves and the ground truth leaves. Our pre-training was producing one embedding per image, but we see that even with just 10% of labels, we already commit less than half of the error committed by the network without pre-training. We can also notice that this is consistent no matter how many labels we use. We also have a qualitative image to show our approach helped boosting the final performance on the task. In this video, I presented a domain-specific approach for pre-training, and I showed that the more domain-specific the pre-training is, the more it boosts the performance. We evaluated the approach using different perception tasks in the agricultural domain and showed that our approach works better, especially when in scarcity of labeled data. You can find more information reading the paper, and you can download our code scanning the QR code. Thank you for your attention, and I will gladly answer any further questions.